And we didn't go in depth into statistical machine translation in the previous lecture. What we looked into were really high level, main conceptual issues like, having that parallel corpus and alignment models, etc. But in practice, the best SMT-based translation models are extremely complex. And, from the 90s to about a few decades, a lot of human effort and were put into this. And usually these systems were maintained using lot of engineering, large number of engineers with hand-engineered features, etc. So to describe the paradigm shift that neural machine translation brought, if you consider that how quickly it became the mainstream de facto production system, then it's really amazing. So in 2014, the first seek-to-seek neural network-based translation paper was published by Ilya Sutskever et al., who was also a grad student here. And then within 2 years, Google Translate switched from SMT to NMT, and by 2018, all production systems had switched to neural machine translation. So what was like a fringe research attempt by a group of few researchers replaced de facto systems that has been there for decades and maintained by hundreds and thousands of engineers. Neural machine translation is truly the flagship of natural language processing deep learning. And even today, it continues to thrive with many improvements over the vanilla model that we will go over today. So the first difference with neural machine translation is that now we do away with the whole noisy channel rigmarole of getting language model and a translation model. So remember that in the noisy channel formulation, we're trying to decompose our target language by first finding probability of F given E and then doing language modeling in probability of English, etc. But in neural machine translation, what we say is that we don't care about that. We'll just optimize end-to-end using our argmax MLE objective, which is like given French, we want to get English. There are a few papers that do exist that try to use noisy channel model for machine translation objective, but that is really not not the dominant and most promising direction. And just optimizing over this, we get functional systems that outperforms SMT by a large margin. Okay, so in neural machine translation, how do we solve the alignment? We do not remember that one of the main problems was that languages are never one-to-one aligned. And in statistical machine translation, the way we try to solve this is by introducing additional parameter or additional variable A, which is alignment, and then trying to look at all possible alignments between the two languages. And but in NMT, we don't do that. We just use the MLE objective, and the way it works is that we just use an encoder, which produces a representation of our source language, and the decoder takes that latent representation and then generates a target sequence in the target language. Another conceptual understanding is that why specifically like this encoder-decoder model, why not just train an RNN that we have seen to output a translated token from the source token, right? So remember, we could have had we could do POS stagger, you take in a word and then you say whether it's an adjective or noun or whatever. In the same way, we can have a source token and then output a target token, and that's it, we're done. But as you can see that this may work the La Bruja translates to witch, but if you take in another, an adjective in Spanish, that the English translation, the witch green, does not make any sense. So this comes from the language, different morphological differences in language that we have seen. So this doesn't work. Another example problem is the source and target sentences length. So we have also seen this example where the Spanish these 3 words translates to just 1 English word. And there's no way we can capture this. And we cannot just assume that the source sentence length and the target sentence length are going to be the same. So it's a very extremely limiting restriction. So that's why the motivation between encoder and decoder comes into effect, so that we don't have to care, like, the source and the target can have variable length. We don't care. We're going to separate the responsibilities. The encoder is going to deal with encoding the source sequence, and the decoder's job will be to take that, latent representation and then generate a target sequence of arbitrary length. So this is a high-level architecture of a vanilla sequence-to-sequence model. And as you can see that this part over here, we've already seen, this is a vanilla unidirectional RNN of 1 layer. And it goes left to right. And as you can see that it's taking in the input sequence in French and producing hidden states. And at the final hidden states, it is outputting the latent representation of the entire sequence, and it is handing that over to the decoder. The decoder is taking that, and then it's outputting a logits or probability distribution over the entire vocabulary, and then you're passing that on to the next time step where it's using the previous word and then outputting and so on. Like it's, yeah. So here the decoder is conditioning on all the French word sequence, which is represented by the last hidden state, H5. And it's also conditioning on the previous output words that it has generated, okay? Yeah, so there are many variants to this model. This is a vanilla conceptual model. And notice that, as we said, that we're optimizing for our MLE objective, which in our formulation changes to probability of the best English sequence, probability of E given F. So there was a question earlier to this class was that, the conceptual confusion over why we need the noisy channel formulation in statistical machine learning. And then, the answer is that, we looked into the alignments. There can be different alignments, and the order information needs to be there. But using this model, we get rid of all that. We're just focusing on what makes, I guess, more intuitive sense. Okay, so given French, give me English. That's it. Yeah.
In this example, this means you still get exactly the same numbers of the words for translation?
Yeah. Yeah. Isn't this simple to understand? But yeah, we could have anything else. Yeah, I guess, yeah. But it's just an example. It's a simplified example. So the question is that, okay, so there are same number of words, like is that one-on-one mapping? But even over here, friendship, magic. Yeah, it's probably a very simplistic example. But the idea is that you could have had a decoder which had more words in it. It doesn't matter. Because as soon as you cross over from the encoder to the decoder, you're handed off to the decoder the latent representation. The decoder will start using the variable t instead of s, which means like it can be a different length. So yeah, was that a question?
Yeah.
Okay. Okay, so this slide also appears at the last page of your assignment to handout. This is just to normalize the notations that we'll be using in this lecture and in the assignment going forward. Yeah, so everything is pretty much self-explanatory. You have source sentences or source sequence denoted by F, and target is E, and X and H is the hidden state. They're embeddings, and to differentiate between the encoder and decoder, we use a tilde. So X tilde is the input to the decoder, and H tilde is the decoder hidden state, okay? And as you see that, like here, S denotes the length of the input sequence, and T denotes the length of the decoder sequence, meaning that they can be different. The last 4 are from attention, which you will see in the later part of the slide. There is a typo here. This E should be A. We're using A as the attention score. But apart from that, yeah, it's use this as a reference for the notations. So let's delve down a little bit on each of the components. So the encoder, as you've seen, that it's given a source text, and it first gets the embedding using embedding function, which is T. And and then so then basically, like in usual fashion, you have this input source sentence, let me test the magic, and that gets converted. You get the hidden states, and you pass over to the decoder at the last hidden state, H4 here. So the decoder is where the magic happens. You sample a target sentence word by word. By sampling, the decoder has a feed-forward network at the very last layer, which outputs logits, which are probability distributions over the entire vocabulary, and you sample word by word. And in the base case, so in the bottom, let's go over a quick example. So you have H4 coming in from the encoder, and as the first word token, you have a start of sentence sequence, and that goes to x tilde 1, which is the input or first input to the decoder. That produces the hidden state h tilde 1 for the decoder, and then that produces a probability distribution for the first word, and we get y1, and that is fed back as an input to the next time step. Okay. Now note that in the first input to the decoder, we don't have a word. We have like a deterministic symbol S over here. And the reason is that like we don't know what the word is yet. Like we're given this latent representation of our input sequence in French, and then we're trying to predict what is the English sentence. So we don't know what the first word in the English language is. So we have to predict it. So we have to offset this by 1, okay? And yeah, so similarly, like x, that's the input, and then the next hidden state, next word probability distribution, you get y2 and you fit it, and so on. And this goes on until we get an end of sequence symbol, and the decoder stops. For training the system, we train using maximum likelihood estimate. And we use autoregression, meaning that the decoder does not see anything to the future. It can only see to the past, okay? So the MLE objective is we're trying to maximize probability of our English sequence given French sequence, and we're trying to maximize something which is equivalent to minimizing the negative of that. So we minimize the log probability of y equals to English given French. And that is summation at the bottom diagram. You can see that one example where this becomes a summation of negative log likelihoods. And notice this, the condition here. So this is the autoregressive property that it is conditioned on only the previous tokens that has been generated, and all the input words or input tokens. Cool. Any questions? Yeah. Yeah. So the reason we use log is because log is monotonously increasing function, so it's a good proxy of the actual probability. So if I say that, like, I don't know, I mean, max of something is same as max of log something. So it's just for computational benefit we use log. Yeah, because it doesn't change the logic. It's always monotonously increasing. So you can replace it with log. It's easier computation. Yeah. But the relation is same, like log x plus 1 is greater than, yeah. So, and you understand why we use the negative, right? Okay. Cool. Okay, so the concept of teacher forcing, yeah. Mm-hmm.
So the input to the decoder would be that representation only. So how do you sample different input to the different?
No. So dimension-wise, like the dimension of this is the same as the dimension of this. Like everything, the hidden states have a dimension, let's say D, and that is same across, right? So is your question that what if it's a different, the representation dimension remains the same, right? So let's say you represent a word using like a 512 dimension, vector, right? So that 512 is not changing. Does that make sense? Or what's the question?
So suppose at the second step there is an input friendship, right? So how do you sample that from the representation? It will remain the same.
Oh, okay. So this Y1 will give us, let's say, friendship, right? So we have a probability distribution here over all the English words, and friendship has the highest probability. We pick friendship, and then we pass it through an embedding function that embeds friendship into a vector of dimension D. That vector is going in as an input to the decoder next step. Okay, so yeah, does that make sense? So yeah, there is an implicit embedding function. We're not, okay?
And what if the word predicted itself is wrong? Suppose.
Very good question. Very good question. As I always say, the best questions are those that lets you segue into the next slide. Okay, so teacher forcing is a concept that happens only during training. Now imagine, as this gentleman suggested, that what if this guy that we predicted, instead of friendship, this is enmity or some other word. How do we use that? So that's where the concept of teacher forcing comes, that saying that, okay, so we will remove this recurrent connection. Instead of feeding back the prediction, we're going to feed in the ground truth, which is friendship. So here, our x tilde t was predicted output. Let's say this is enmity. With we're going to replace enmity with ground truth, which is friendship. So it's correct, and we don't have to deal with that question. Now, one thing is that even if it was enmity, it doesn't matter. It would still learn because of the loss would be high. You'd back propagate the loss, and eventually it will learn to predict friendship instead of enmity. But it will take longer time. But by using ground truth, we're making the training faster. Okay. But there's a caveat to it. The problem is that then if you do teacher forcing throughout your training, then your model is never learning what's wrong. Like it's only like, oh, it's always like we're never allowing the decoder to fail, and that could create what we call exposure bias. So it's not going to generalize well to like other situations. So there are other techniques of making, like usually in production or practice, what we'll do is like you'll have some warm-up steps where you're teacher forcing, and then you'll like stop feeding it the right ground truth values. So it will just basically, it will start feeding back its output back to the decoder input. But teacher forcing is the idea is that you don't feed it your prediction, you feed it the ground truth. Okay? Good question. Yeah.
So, what are like multiple possible translations of the same thing?
Of course. So that is coming from your corpus, right? So we're training it against the ground truth is what? We have two parallel sentences that says amity is friendship, right? So you're just, that depends, I mean, the system is learning it from your large parallel corpus. Okay. All right, so let's look at, we'll segue into attention next. So like, let's look at some motivations. So this motivation you've already seen is that, with this vanilla architecture, the problem is in the last layer, right? So again, the last hidden state of the encoder has a very large responsibility. It has to remember everything, right, that came before it. So it's a short sentence over here, but remember, like if it's a very long sentence, then it has to encode all that information and hold it to it and then transfer it to the decoder. And that's what the attention idea is that, okay, so instead of just depending on the last hidden state of the encoder, what if we could look at all the encoder hidden states? So then we don't have the dependency on the last encoder hidden state. So I want to pick at H2, I want to pick at H1, and I want to pick at H3. And then I'll decide that given I am at time step T, which one of this previous word tokens in the source language is most important or relevant to me. I'll decide that. So that's exactly like what attention does. And you'll see this diagram appearing like, in many papers or blogs. So essentially the idea is that, for example, European Economic Area, Zone Economic European, and you're basically, that order, you have attention and you have relative attention. So, okay, so these three words are important. So maybe like you have this relative weight to these three words, and you can pick the entire source sequence. So we combine input from if our input sequence length is S in a context-dependent way. Okay, so in this slide, you already know this part. Like, so forget that CT, which we call our context vector, exists. Okay, you already know this, that for the next decoder input, we're going to fit in the previous whatever, whether it's teacher forcing or whether it's the output. We're going to feed in the embedding of the previously predicted word. The only thing novel or new is this context vector. And the attention mechanism is all about like how we calculate this context vector, and that's it. There's nothing new about it. So how we do this is just simple three-step process. First, you calculate the attention score. So you have H tilde T. So let's consider we're at time step T. We have our, actually would be at time step T plus 1. We have a decoder hidden state, H tilde T. And consider this as a query, and I'm going to look at all the values. What are the values? The input source sequence, which is denoted by H1 to S. And I'm going to compare against each of them, and then I'm going to create attention score, okay? That's this part. The second step, like whenever you're calculating something, you got to normalize it. That's where our friend softmax comes in. You normalize the weights. And then you basically take all the input hidden states and you add them together based on their weight. So any word that had more weight, for example, when it's area, zone will have higher weight than hamburger. So you just add them up, giving more weight to the correct word. That's it. And once you have the CT, we do as we always do. We just concatenate it with our input. Yeah. That is exactly it. Yeah. So the score function over here, okay? So what we're showing over here is just dot product attention. So we're just like, dot multiplying the two vectors. Yeah.
So the hidden state, that's the hidden state from encoder or hidden state from decoder.
Yeah. So H1S means the encoder, all the encoder hidden states from word. H tilde. Yeah, so H tilde T is one decoder hidden state. Okay, so I'm in a decoder, I'm at one time slice in a decoder, and I'm looking at all the encoder hidden states.
So you find the similarity.
Exactly. So you're just gonna, and you repeat this for each decoder step, right? So that means it's like quadratic time, like at each step you're looking at all the encoder hidden states, and again, you're moving encoder hidden states.
And the 1 to S means you only be able to looking at all the previous hidden states, not the future hidden states.
Which one?
So it's like the 1 to S, the hidden states 1 to S. That means you're only looking, so S should be smaller than time step T.
In number 2?
Number 1.
Number 1, this
So
S?
that 1 to S means the S should be smaller than time step T, right?
I don't follow.
So you have a time step T.
T, yeah.
That
So
means it's like the T time step you predict that word. And then 1 to S means all the previous positions, right?
in the encoder.
Yeah. And
Yeah.
so that means it's like you can now look at the word after the time step T.
No, but when we use T, we're into decoder space. We're using decoder's length. We don't so basically T could be larger than S, right? So it doesn't matter. So that doesn't necessarily mean that decoder is looking at previous. We're looking at encoder. Encoder is in the past.
Okay, so the S will be the length for the total hidden state in the encoder.
In the encoder, yes. Yeah. So S is in encoder, T is entirely in decoder. So we're not looking in the future. So the score function, so this is one example that you can use in your bonus for your A2. So it could be something vanilla like, just a dot product attention, but there are many variants to it. Another example is that multiplicative bilinear attention, also called the Luong attention. So here you have a weight matrix between the hidden states, and then so you can also learn that weight matrix as well. So it's just one example. There's a few other variants to it, and the reason I'm showing this here is that so that it's an option for you to explore in A2 bonus if you want to. And another helpful mind map going to the forward slides is the whole introduction of the query key values and names that you see so often in this paradigm. So one conceptual mind map could be, you can think of the decoder hidden state, H tilde T, as a query, as a question, that attends to all the encoder hidden states, which are values. Any questions? Okay. Okay, so quickly go over this, just one example of attention so that it sticks. So we are in decoder time step 1. And in the first step, what we're going to do, we'll, and these are encoder hidden states. So first we will calculate an attention score for the current decoder hidden state against all the encoder hidden states, H1, 2, 3. Okay, so we got 3 attention scores. Okay, and the next part is always we have to like standardize or normalize these values. So we take a softmax. Okay, so that's our weights. And the third step is we create the context vector by multiplying each of these encoder hidden states with their corresponding weights. Okay. And once you've done that, then we get our context vector T. And the last step is simply concatenating that with our previous output word prediction, okay? And that's our input to the next step of the decoder, okay? Is that crystal clear? Cool. All right. So before going to details of this slide, let's just do a mind map. So essentially think of that the undergrad department has asked for a student feedback of this lecture, and I have 1 page to submit it. And so let's say I pick someone. What's your name? John. Okay, so I ask, like, John and I are good friends, and I tell him to give me a good glowing recommendation, and he fills up 1 page, and I give it to the department. But that's not a very representative sample of the actual feelings of the class, right? So I need more feedback. So what I do, but I still have 1 page. So the only way I can do this is that, like, I get more, like, n more feedbacks, let's say 8 more feedbacks from 8 different students, and then I summarize John's feedback 1 page into 1 paragraph, okay? And I do everyone's giving me 1 page, feedback, like give me 1 page feedback. So I take, let's say, 8 feedbacks, and I summarize each of those 1 page into 1 paragraph, and I have 8 paragraphs which I can fit into 1 page. And then I take that page and I give it to the department saying that, hey, here's the actual feedback of the lecture. And multi-head attention is conceptually, like, that's the idea. So you're doing everything the same, but now you're going to compact everything. You're going to have a denser representation of the hidden states. And how can you get a denser representation? One simple way is to just project them into a lower dimension. The way we can do that is multiplying it with a weight matrix, but with the dimensions shortened. So if you do a multiplication, you should be convinced that what we're doing here is that we're condensing our hidden state vectors, H tilde and H, into a lower dimension, D over N. And so you already get the idea, right? So if we have, for each of the head, we have D over N dimension, and we have stacked them or concatenated them, then we're still maintaining D, right? That's the idea. So basically once we have this dense, and then if you're convinced with number 1, then the rest is essentially exactly the same thing that we did, but we're just using a notation N to denote which head. So if there's 8 heads, then you're gonna have 8 of those. So now, can someone tell me that what will be the dimension of C NT minus 1 here? What is the dimension of this guy? Who can tell me? Yes, that's correct. So if you have, if this is D over N, and if you have N of them, what would be the dimension of this guy over here? Sorry, this. So D over N, you stack N of them. D, okay, good. And then, so that's the last step. You just combine all the different context vectors, and then you apply a linear transformation using matrix Q, and basically, concatenate that with this part is the same as before, okay? So that's our x tilde t, which is our input to the next decoder step, okay? Does that make sense? Here, when you're doing your assignment, just be very clear about the dimensions, okay? So basically, like, so when you have multi-headed attention, if you have, like, let's say 2 heads, so just think about in terms of, like, the dimensions of each of the context vectors, and when you concatenate them, remember the output, like, dimension stays the same, but you're packing in more information. So you're basically packing more information. So you have n different latent space representation of the same information. Before we had one single head, we had one latent representation. Now we have 8 or n different representation. We combine them and give it to it's the same idea as the lecture feedback example of one page that I gave, intuitively. Okay, so any more questions? Yeah.
W and W23 will also be learned through the lab.
Yeah. So also it will be covered in the tutorials. So here for pedagogical reasons, I have included, like, usually you'd have one large weight matrix and you'd use view. Like you'll just, like, use view, like you'll select a particular portion and then do the multiplications. But that's, let's not talk about that here. That's more tutorial stuff. Okay, so attention advantages, it really was a paradigm shift. It improved NMT significantly. It solved the bottleneck problem, helps with the long horizon vanishing gradient problem by providing shortcuts to all the distant states. And it also makes the model somewhat interpretable. So at the bottom right, if you look at the figure at the bottom right, you'll see something that is reminiscent of the word alignment matrices that we see in the SMT lecture. This is not exactly word alignment, but you can think of it as a sort of soft alignment. And the network learns it by itself without any explicit training. So yeah, it gives us With that, let's move on to transformer networks, which is, after the paper coming out in 2017, it has really been the de facto architecture for all modern neural network and large language model architectures. And if you summarize the core idea behind it into one word, it would be just, it replaces all the recurrent connections with simply attention. And we'll see what that means in a bit, but in terms of the results, as you can see that at the time of its release, it was able to get the state-of-the-art results on neural machine translation tasks. So this is English to German and English to French. It beat over all these models which were very complex, and it was very simple, and it had state-of-the-art performance at a fraction of the training costs, if you consider the training costs between these large complex models and transformers. And the reason it was able to do it is because of this one core idea, which is to remove the lateral recurrent connections that we have seen so far in RNNs, okay? If you look at the bottom left diagram, you'll see that each node of the hidden state over here has 2 arrows coming in, which shows the number in green shows the time step that is required before it can reach that state. So obviously, if it's a recurrent architecture, you'll have to wait for the previous node to be calculated, right? Before you can calculate this, right? So before you can do H3, you have to have H1, H2, and so on. You get the idea. Yeah, so basically, if you cut those recurrent connections, then you have this transformer attention-only architecture where you can see the entire sequence in the first step, and you can also parallelly, like, you can calculate the weights from each of this previous layers nodes, and you can calculate it in the first time step. You don't have to wait, right? So you can calculate H3 at the after first time step. So that's the idea. So this is not showing all the connections, but if you look at the highlights, so here you can calculate H2 from all the bottom previous layers nodes, and then you can also calculate, similarly, you can calculate H4 at the time step 2, because you have all the hidden states from H1 to H4 after the first time step. So that's the conceptual idea. Okay. Okay, so now I want to explain the terms query key values in an intuitive way because this is very prevalent in transformer architecture explanations in literature. So the idea of query key value actually comes from information retrieval. So think of it that if you only had manual storage, so if you're given the task of handling Acorn and where you have three kinds of information, it can be your personal information, it can be your financial information, or your academic information. Now, if you didn't have any electronic storage, you'd have to have like, three drawers in a filing cabinet. Each of the drawers would have a label on it, academic, financial, or personal, and then you'll dump all the information with respective categories. And if I asked you a question, then you'd first take my question, and then first thing you'd do, you'd figure out that which of these three drawers I should be looking into. And the way you would do that is by comparing the keys or labels on the drawers, and then whatever the query is. So if it's like current academic standing, I'd look into the drawer that had the label or key academic, right? So this is essentially where the query key values come in. So first you do a comparison between the keys and queries to find out where to look for it. And this could be dot product attention or any other attention function that of your desire. And then once you find out that, okay, it's in the drawer and it's this in the filing cabinet, and then we'll just go into, inside the documents inside that folder, and then you'll basically use them as your values. Okay, and this is where this equation comes from. So first you're getting think of this as a dot product, scale dot product attention, this part, okay? So query, key, and then this is like just a normalizing constant to, make it more computationally feasible or, yeah. And then you do a softmax to normalize those scores. And then you pick the highest score, which in this example, it would go to academic. And then you're basically getting all the values or the documents inside that in that folder. And yeah, so any questions about query key values? So usually what you'd do in our previous example, the decoder usually has the query, and your encoder has the keys and values, which is also called as memory. So the encoder contains, so think of the encoder as the filing cabinet. It has the keys and the values, okay? And in technical lingo, it could be the memory. And whatever the decoder is doing, decoder is querying the memory, that this is which part of the memory should I look into, which part of the memory I should look into. So when you look in the technical documentation, always like the decoder has the query and the encoder values are our keys and values, okay? Sorry, did I see a raised hand? Yeah.
So for the first question, like what would be the queries, what would be the values?
Oh, so I mean this one?
Yeah.
Okay, so this is, first of all, okay, so in this case, so you'd have, are you trying to say like in this equation or in general, like, with the query and key, you'd find out, like, are you talking about the real world example or? In this example, you just find a folder that says academic on it, right? So you have the key academic. So it would just basically, this query key multiplication would give us academic would turn out to have a probability of 0.90, and these two guys would probably have 0.05 or 0.05, right? So then you just pick this academic, you'd open the drawer, and then these are your values. Like is there?
I guess I don't understand why we have to have keys and queries, but can't we just compare the keys or compare the queries of each?
Yeah. Well, each. What do you mean? You are. So in order to find the right drawer, you are actually comparing all of the keys, right, with the query, because without doing that, you don't know what's the right key. So you have to think of it like the encoder hidden states. They are your sort of keys, and values are the representation. Very, very roughly speaking, I'm not being, so with the decoder hidden state is like sort of, this is my query. The query is my decoder hidden state, and you're just going and comparing with the encoder hidden states. and then you're seeing that which one has relatively more important, right? And then think of them in drawers, and you're going to look in those drawers to get the values, and you're going to ignore the drawers that are not relevant. So yeah, I mean, query key, I mean, you can, I don't know, if the question is about why they're termed the way they are, I mean, that I cannot answer. I mean, okay. So so this one is high-level depiction of the transformer architecture. I'd like to say right away that this lecture does not cover the complete technical details of implementing a transformer architecture, because that would be a lecture of its own. But I'll just gloss over the main components. So you have the encoder and decoder blobs, same as before, and each of this is like one layer, and you have like identical layers, usually like, you know, it could be 6 layers stacked on top of each other. But in each side, each of this layer, you have sublayers. The encoder has 2 sublayers, which is the self-attention and a feed-forward network. And the decoder has 3 sublayers. So you have the self-attention, and you have a cross-attention, and the feed-forward network. The intuitive understanding is that initially in the self-attention phase, both in the encoder and decoder, the sequences sort of like pay attention to each other. They're just like, you know, percolating up. And then after some time, they talk to each other. And then the decoder, after talking to the encoder hidden states, it outputs the probability distribution. So in the encoder, first it uses self-attention, which is depicted by this blue arrows over here. And you already know what that means. Self-attention is just basically, instead of what we've seen H tilde, it's just attending to itself. So each of the states is looking at itself. And as you can see, that this would produce like S context vectors, and that would be your hidden state for the upper layer. Anyway, so you'd be attending to his own hidden state, and then percolate up. In the decoder, same thing. First, you're doing self-attention with each other. And here's a star because it's masked self-attention, which just means that it cannot see to the future. Okay, so the autoregressive properties maintain. So the way it's done is that you mask out all future sentences using like usually like a value infinity or negative infinity or something, very low number. And after that, it does attention with encoders. So this is the orange arrows over here. So at this stage, the decoder and encoder is talking to each other. And it's then after that, decoder is outputting like, you know, the output probability distribution from where you'd get your next word prediction. Okay. So the transformer autoregressive property is maintained using 2 things. One is the masked self-attention. So essentially when the decoder is attending to its own sequences, it can only look at sequences that has been previously predicted. So it cannot, and the rest of the words in the future, they're masked out. And also like from during decoding, the first word is like a placeholder sequence, which is the start of the word sequence. So we're at the first step, we don't have any, we're not given anything. We're just predicting on a placeholder token, which is our start of the sequence token. And we do this until the decoder does this until it gets end of sequence symbol. Okay, so now another problem with this, yeah.
As we progress through time, like does the dimension of the Z vector, like in the previous slide, change?
Did the dimension change in the previous slide?
And like as we progress through time, because like as we progress through time, we can like incorporate more of the like H tilde vectors into the attention.
No, you're not. You're still working with because the dimension doesn't change. Like maybe whatever is in the future, it's masked out, but there are some values for it. So it's basically like masked out, like, but it's not changing. The dimension is not changing. So we know that in language, the word order matters. And if we are going to do something purely parallel architecture like this, then this would be permutationally invariant. So the attention values of this guy would be equal to any possible permutation or ordering of a sorted sequence, right? So how do we, but how do we sort of delineate, or how do we maintain the word order. And the solution to this is that we will infuse some positional information to our embedding. The way we can do this is by adding a positional encoding to our hidden states. And this positional encodings depicted in green over here has the same dimension as the hidden states. So you can just do a simple addition. And this, from this positional encodings, the ordering is induced or infused by inserting like sinusoids in the dimension of this positional embeddings. So here position is, pos is the word token position, and the I represents the dimension. So think of like if you have a word, if you have a batch of, or like if you have word of dimension 1024, so each of the dimension, like the positive dimensions, you're gonna insert a sinusoid, and for the odd and even positions, you can insert like sinusoids, and there will be a regularity to it. So that sort of conveys the position. There are many different ways to inject this sinusoid. This is just one of them. But essentially, yeah, the positional embedding is an embedding of the same size as the hidden state embedding that you can just slap on it and to convey some positional information. Runtime complexity, this is a very simplistic, just more of an observation. Yeah.
Yeah, for the previous slide,
Mm-hmm.
after encoding this way,
Mm-hmm.
how could you decode out the positions?
Mm.
So basically just adding a
So remember that,
variable here.
right, so remember that this positioning, like this is true for all the sequences. So you're training on it. So it's basically the same way you could decode, I mean, you still have like your conditioning on an embedding that just has some positional regularity to it. And so you're decoding based on that embedding instead of just the embedding. So,
Yeah, I understand you include the position information into the hidden state.
mhm.
But then it's like all these hidden states using attention stuff will go into the decoder. But
Right.
decoder is taking the information is like concatenate together.
Why don't we take it after class? Like maybe I have 2
Yeah.
more slides. Let's finish that, and then I can come back to it. Okay, so the main takeaway from this slide is that the runtime complexity is quadratic to the input sequence length. The reason is because at each decoder step, we're looking at all the encoder states. And yeah, so this is a problem because although transformers now allows us to train fast, but the decoding is very slow. And the ways to address that, how can we address this quadratic time? This is an ongoing research area where there are many techniques to sort of make it like, like linformers, or how can we make this quadratic time a linear time, etc., or have different kind of architectures. So it's an ongoing research area, but this is one caveat of having purely attention-based model is that the decoding time is quadratic to the input length. And so BART is essentially like one of the most dominant large language model architecture. And this is, BART's architecture is like the transformer architecture. If you take the transformer architecture and then just cut away the decoder part, it's just the encoder part. And before in transformers, you've seen that the last layer of the encoder is feeding to the decoder for the decoder to output something. But here, you can slap on a feed-forward network, and then it takes the encoder output and then outputs some probability distribution. And in order to, like the prediction task is mimicked something called masked language modeling. So you have an input sequence and you mask out some of the words in that sequence. And it's your language, your encoder is learning to predict what those fill in the blanks or what those masked words are. So in that way, you can actually model language just using the encoder part. And this is this is great because you can now pre-train a very large model with lots of data, and then you can use that pre-trained model for downstream tasks. One example is that the BART, where they use the pre-trained BART to like basically and add a decoder, which takes in the encoding, and then now whatever your downstream task is. If your downstream task is, let's say, neural machine translation, then you'll train your model to output the next token in the target language and then basically train for it. But the advantage is that you can slap in this pre-trained encoder and pre-trained decoder and then fine-tune using whatever your task is. So this is how most of the like large language models, pre-trained models are being used for different downstream tasks. All right, so we'll start from, we'll look at decoding evaluation next class, but I'd like to stop the NMT here. Thank you.